Hello everyone. Welcome to 41076, Methods in Quantum Computing. My name is Min-Hsiu Xie. I'm your subject coordinator and lecturer in this semester. This is a recorded lecture, so if you have any question regarding the content, you can raise your question during the tutorial section right after the class. Here we are about to start the first submodule of Lecture 1, Introduction to Quantum Mechanics. The first submodule will introduce basic linear algebra in Dirac notation. The outline in the submodule includes the Dirac notations, how to define matrix functions, how to define tensor product using Dirac notation, and finally, how to compute trace and partial trace. Throughout the lecture, we will denote curly H a d-dimensional Hilbert space, if not stated otherwise. A vector V in the Hilbert space H is a column vector with d elements, where each element Vi could be a complex number. We can rewrite the vector V as the sum of each complex number times the corresponding computational basis Ei, where Ei is a zero column vectors except a 1 at the i's plus 1 location. However, this is not the conventional notation used in quantum information community. In our community, we will use the Dirac notation, the cat notation, to denote a column vector V. Equivalently, cat V can be written as the sum of each complex number Vi times cat I, the computational basis in Dirac notation. Dual to the cat notation for a column vector is the broad notation for a row vector. Specifically, the broad of V is a Hermitian conjugate or a transpose conjugate of cat V and is equal to a d-dimensional row vector consisting of V0 conjugate, V1 conjugate, etc. The inner product of two d-dimensional vectors u and v can be written using bracket notations as follows. Similarly, we can easily represent the outer product of u and v this way so that the ijth element of the resulting matrix is equal to vi times uj conjugate. Let L be a linear operator defined on the Hilbert space H. We will denote by curly L of H the collection of all linear operators in this subject. Equivalently, a linear operator have a matrix representation in fixed basis. Here we are writing the linear operator L using the computational basis Ij. Then the ijth element of L can be explicitly computed by sandwiching L by bra I and cat j. A linear operator H is Hermitian if H is equal to its Hermitian conjugate or transpose conjugate. Every Hermitian matrix has a spectral decomposition into eigenvalues lambda I and its corresponding eigenvector nu I. A linear operator P is positive or positive semi-definite if for every vector V in Hilbert space H, the inner product of P acting on V with V itself is non-negative. Note that every positive operator is also Hermitian. Hence, this definition also implies that the eigenvalue of a positive operator must be non-negative. Finally, we denote by curly LH plus the collection of all positive operators in Hilbert space H in this subject. For any real value function f and a Hermitian matrix H whose spectral decomposition is given here with eigenvalue lambda I and eigenvector nu I, we can define the matrix function f of h as follows. The output of the matrix function f of h has the same set of eigenvectors nu I with the new eigenvalues f of lambda I. Once we define matrix functions, we can talk about their convexity. We say that a matrix function f is convex if for any Hermitian matrices A and B and P in between 0 and 1, f of 1 minus P times A plus P times B is less than or equal to 1 minus P times f of A plus P times f of B. The less than or equal to here refers to partial ordering. We can also discuss monotonicity. We said a matrix function f is monotone if whenever matrix A is larger than or equal to B, then f of A is larger than or equal to f of B. Here, we will introduce definition of tensor product. For two vectors v and u with dimensions dA and dB respectively, the tensor product of these two vectors is a vector with dimension dA times dB. The ket I tensor ket J will become the new computational basis in the joint Hilbert space HA tensor HB, or we just call HAB. The definition of tensor product of two vectors can be easily extended to tensor product of two operators or two matrices. Given two matrices L and M with size dA square and dB square respectively, the tensor product of two matrices will become a matrix of dimension dA square times dB square. Here, IJKL will become the new matrix basis in the joint Hilbert space. Here, we will mention a few useful properties of tensor product. Firstly, multiplication of two k-fold tensor product A1 tensor A2 tensor up to AK and B1 tensor B2 up to BK is equal to A1 B1 tensor A2 B2 tensor up to AK BK. Secondly, the inverse of a k-fold tensor A1 tensor up to AK is equal to A1 inverse tensor A2 inverse tensor up to AK inverse. Finally, the Hermitian conjugate or transpose conjugate of a k-fold tensor operators A1 tensor up to AK is equal to A1 dagger tensor A2 dagger tensor up to AK dagger. Trace is a linear operator that takes linear operator defined on the Hilbert space H as the input and the output a complex numbers. Specifically, the trace is defined on the linear operators or a basics, namely the outer product of the computational basics JK in the Hilbert space and output their inner product, which is now a number. The definition of trace extends naturally by linearities. Specifically, the trace of a linear operator L is computed as follows. Recall that L has the matrix representation in terms of the computational basics I. Because the trace is a linear operator, we can interchange the sum and the factor Lij with trace. The third line follows by the definition of the trace in the previous slide, and we can extend the ij's element using this inner product form. Finally, the inner product of computational basics I and j is just a delta function that equals to 1 if and only if I equal j. Hence, we can reach the final expression, that is, the trace of a linear operator L is equal to the sum of its diagonal entry in the matrix representation. The partial trace is a linear operator that takes linear operator defined on joint Hilbert space HA and HB as the input and the output of linear operators on the Hilbert space HB. Specifically, the partial trace over subsystem A is defined on the linear operators or basics, namely the outer product of the computational basics ij in Hilbert space A, tensor the outer product of the computational basics KL in the Hilbert space B, and output the matrix or the outer product of computational basics KL times the inner product of ij, which is just a number. Thank you for listening. This is the end of the submodule Linear Algebra in Direct Notation. We will continue our second submodule after a short break.